So our meeting is called some particular aspects of automorphic forms. So, and we have a nice abbreviation also. So I've given the title of the talk in same spirit, except I'll talk a little more about some different aspects, namely spectral and analytic. The talk will be more in the line with the representation theoretical aspects, not so much with the automorphic things. So there's a word called trace formula. Some of you might be familiar with it, some of you may not be. Let me start with one motivation which is slightly different from the things that we have been looking at so far. So in Fourier analysis, there's a concept called, or a formula called Poisson summation formula. So what you do is that you start with the Euclidean space, pick up a function which has some suitable decay properties. So we'll not go into that aspect right now, but sufficient decay properties are assumed, and then you think of the average of the function over a given lattice. So lattice for us will be, in this context, the discrete subgroup of Rn of the full rank, which will be a finitely generated abelian group without torsion. And there's a concept of dual lattice, which one can define using the standard inner product of Rn. So what it says is that the spectral average and space average are same. So you start with this function, vary the points over the given lattice, and look at this average. It will converge because f has a nice decay property at infinity. On the other hand, because of that property, the Fourier transform, the way it is defined, will also have the sufficient decay properties, and then you can make sense of the left-hand side. And the Poisson summation formula says that they're equal. Now, you don't see trace or representations here anywhere. You will later see a slight generalization of this in our context, and I'll get back to this that time again. So the idea is that some sort of integral is happening on the right side of this equation, where you are averaging the values of function over a certain set. On the left-hand side, you are taking average of Fourier transform, which is going to be related to representation theory of Rn and generalized to some other groups in my talk. So this is one kind of motivation from Fourier analysis. The next one is about finite groups, which many of you are surely familiar with. So the formula for the character of the induced representation of a finite group, subgroup of a finite group, can be written in terms of the centralizers of various elements and conjugacy classes and so on, and the inducing character. So this will be corresponding to a representation of the subgroup, and then you induce it to G and you get this. So again, here you see the representation theory on the nose, but how is it related to operators and traces? That we'll relate to in a minute. So very brief idea is that you think of this thing as getting evaluated at G, and then equivalently you can think of the indicator function of singleton sets and think of this as an operator acting on a space of functions and evaluated at one particular function, which is the indicator function, and then you calculate its stress. That's how the left-hand side will look like. Right-hand side will have similar kind of integral. It's a finite sum, so special case of integral, and which is coming from, again, functions on subgroup and points of the group. So this is also can be taken in the same spirit. Space average is same as spectral average by appropriate use of functions and convolution operators. Now let me go to the main setup that I want to talk about today. So very broadly or very generally, we are going to think about locally compact groups with the Haar measure and so on. So that's the machinery one will use. The case of interest for my talk will be semi-simple and reductive Lie groups. One can generalize this to a fair generality of locally compact groups, but the automorphic people will be interested in groups with adelic points and so on. So I'll not go that much, go into the adelic setup so much today, but one can define it in the general setup. And one knows what is a discrete subgroup. So one is starting with a locally compact unimodular group. So this unimodular will mean that the Haar measure is left and right both invariant. Unimodular is also used in the context of determinant one condition. So the formula which I stated earlier was really about unimodular subgroups of Rn. But yeah, so now we are going to look at this thing. Left and right Harmajas agree. And then there is a discrete subgroup with this condition. So G mod gamma will be certain quotient space. And then the Harmacher descends on G mod gamma to give a right invariant Harmacher here. One could have taken the other coset space, G mod gamma on the right, then we'll get a left invariant measure. So I'll prefer to work with taking quotient on the left for this talk. And then you can look at the space. So here we are going to assume the volume is finite. So one arithmetically interesting case, which all of you are familiar with, is the SL2Z sitting inside SL2R, which will, where the quotient will have finite volume, but the quotient is not compact in that case. Later, we are going to look at that case in more detail. So now there is a certain Hilbert space we are associated with it. You look at all left gamma invariant functions on G. There will be functions defined on this space, and then this space has a measure, which is finite. So this will, for example, contain all continuous functions on this space, complex valued. But to complete it, we'll have to get the L2 functions, and you get a Hilbert space. And now one of the interesting and more important representation of the group G you have on this space is the right regular representation. So you just translate your function like this to get a unitary representation. So you can imagine that in the interesting cases, G will be like, let's say, SL2R and gamma is like SL2Z. Then the quotient is certainly a large space, finite volume, but reasonably large space. And yeah, and then you'll have an infinite dimensional Hilbert space associated. So we immediately go beyond the finite dimensional representation theory by looking at such things. Now, a slightly easier to analyze case of compact quotient, which will be seen in today's lecture, will be when G mod gamma is compact. So you can assume the measure is a priority measure, the total measure is 1. And now you look at this Hilbert space we looked at. So it behaves very much like, let's say, finite group representation theory or compact group representation theory works, where the whole L2 space itself will decompose discretely, and it will break up as a direct sum of this kind, except it will be not the algebraic direct sum, there will be some completion one has to take. So let's ignore that issue for such a lecture right now. This is well-established theory anyway. Now what you do is that you look at all irreducible unitary representation equivalence classes of G, and then for each of them, more importantly, appears with a finite multiplicity. So this is because we are assuming it's compact. The generalizations of this phenomena also occurs. Maybe in the end I'll get to it in little more details. Now we are going to compare what happens for two different such gammas. So let's start with two. Let me call them uniform lattices, which will mean the quotient is compact. But the definition will go even without assuming compactness of the quotient. The representations, so you look at this definition, basically the L2 representations are isomorphic in a unitary way. So there's a unitary operator which is G equivalent and so on. Such a thing is called a representation equivalence. And here, because it was behaving like finite groups, as I said, the multiplities being equal is sufficient to say that the representations are equal, isomorphic. Yeah, so let's think of this as some sort of spectral equivalence. Spectrum in this context will be the representations which occur in this decomposition. So if they don't occur, then both these will be 0. And if they occur, the multiplities are equal. So in that sense, you can think of them as equality of multi-sets. And yeah, you can define the representation spectrum that way. Okay, so I'll come back to the non-compact case a little later. So the most, let's say, the earliest example of the trace formula which belongs to this kind of class is by Selberg, and he studied the context of discrete subgroups of SL2R, which appear in the modular forms context quite frequently. Although the SL2Z itself doesn't come in that case, but one has the analog of this there as well. And this is just stated as a very famous theoretical result. We'll probably not go into so much what kind of data comes in here, but just to give a broad idea. So here the this sum is taken over elements of this gamma. And now you can think of this gamma also as the fundamental group of the quotient space. So those who have seen the idea of homogeneous spaces, this is our dear hyperbolic plane, either thought of as the upper up plane or the disk model. And then you go modulo this gamma on left hand side to get a certain space. So this space will be, in fact, under some more assumptions on gamma, it will be a two-dimensional real manifold as well as Riemann surface in some suitable sense. And we are assuming compactness, so this will be compact. And then you think of the SL2 R modulo SO2 as the universal cover of this, and gamma becomes a fundamental group. And then you can talk about the differential geometric aspects of this space. You can think about elements of gamma defining geodesic classes in the space. Sorry, this G. No, here on this side, I'm looking at a function, and H will become some sort of Fourier transform of G. So the statement is in that form. One can rewrite it using the so the function for which this is getting applied is G, and H is some transform of G. So in the Poisson summation formula, if you remember, the one side had Fourier transform, other side has the function. So it's of that nature. Yeah, nevertheless, the term that you see here, n of gamma 0 and so on, and n of gamma, they are related to the lengths of the geodesic that you get on this surface, and norm is some sort of exponential of the length. And then you get certain term corresponding to the gamma equal to identity, the trivial constant loop. And essentially this is through, so mu of f will be the volume of the fundamental domain, and so on. And this H will be a Fourier transform. What comes here? So just one line description. So we are not looking at arbitrary functions here. We are going to look at functions on this space. So they are also K invariant on the right side, SO2 invariant on the right side, or they are functions on the upper up plane. Because of that, there is certain theory of Laplace operator and its eigenfunctions, and the eigenvalues of Laplace operator will appear. That will be a sequence, discrete set, and that will appear in this way. And then you evaluate the Fourier transform of the function G at those points. That is how the description of this formula is. Now we are going to look at slightly more general setup where there will be a, let's say, Lie group, semi-simple Lie group at the given to us, and discrete subgroup gamma such that the quotient is compact. This is one case of that. Except for a general function, you don't see Laplace eigenvalues directly, you'll see something else. But yeah, I will probably in the end, I'll relate this with this example. Okay, so now let me talk about the general spectral, Selbach-Trace formula. So the starting data is a discrete subgroup gamma. It has, let's say it's a countable subgroup, and we can talk about the conjugacy classes of elements in that gamma itself. So that is, so to say, a geometric data. Geometric in the sense that they'll be thought of as, let's say, geodesic classes in a certain homogeneous manifold, or you can directly think of them as discrete points with the conjugacy relation between them, and we are going to evaluate certain integrals over conjugacy classes. So in that sense, it is called a geometric data. And the spectral data corresponds to the representations which occur in L2G mod gamma, as you will see in a few minutes. So this is just the general description of what trace formula does. And the idea is that there's a certain convolution operator defined on this Hilbert space, and we will evaluate trace of that. You have to be careful. You can apply the idea of trace and all in finite dimensional vector spaces directly. But for Hilbert spaces, one has to worry about some analytic aspects, whether the trace exists and so on. So under suitable conditions on F, all these things will make sense in the way we have seen. And you basically calculate the trace of that in two ways to get a certain equation, which is called Selbach-Trace formula. So of course, I'm not going to derive the trace formula as such here, but I'll say a few words about this last comment, the calculation of trace, when we go to the setup of our Lie groups. So ultimately, right now, unless I define this object, this is just some mumbo jumbo, some symbols appearing here and there. But the theme is something like this. On this side, you will get conjugacy classes of elements in the discrete subgroup, certain integrals, which I'll come to in a minute, for a few minutes. And this side, we are going to look at those multiplicities of representations appearing and certain, this thing is called character distribution, which some of you, especially the younger PhD students, you may not be familiar completely. I'll define them soon. Yes, all right, now let's stare at this, but we'll come back to this slide later. So the description is here, which I'll skip for a minute. I'll come back to this. So let me just set up the stage for what we are going to see. So we are going to look at the special case of linear connected semisimple Lie groups. The theory works little better than the reductive groups here. So we'll go with this, and SL2R is the basic example of this setup. And now we are going to look at abstractly a concept of irreducible unitary representations on Hilbert spaces. So yeah, so you just want unitary, it's homomorphism from your group to the unitary operators on the Hilbert space with some continuity properties assumed, which I'll not go into right now. And then the space functions on which this stress formula works best is the compactly supported and smooth functions. So you're going to think of your group G as a manifold as well. And you just look at this space. So for example, the linear maps on this space with certain continuity properties are called distributions on G, and we are going to look at such distributions. And the basic operator here is the convolution operator, which I defined here in the general setup, that you start with the function f and think of what pi x does to a pair of vectors in this way. And then you take the weighted average or integral of this times fx with respect to the Haar measure. So just to people who are familiar with the finite group representation theory should connect this with what they know from there. So if your setup is a finite group, then the way I define the operator is nothing but summation f of x. So each pi of x is thought of as a linear operator on the finite dimensional representation space V, and you are just taking the sum, except here the sum will be with some normalizing constant if you want to normalize it as a probability measure. If not, then you can stay as it is. So this pi f was defined there. And now you can connect with the various analysis comments which I made. So here, for example, immediate question will be in the general case, why will this integral be finite, and so on. So all such things are taken care by assuming f is compactly supported, and continuity properties of the representation are also there. Unitariness is already there. So this is the idea. So you keep in mind, those who haven't seen this kind of ideas before, keep in mind the finite group theory, where you can calculate the trace of this that will become the summation fx into trace of this, which is called the character of that representation pi. And here there is no analogy of character of a representation because pi g itself may not have a trace. It's an infinite dimensional. So take the example of trivial element, and this is just the identity operator on a Hilbert space, infinite dimensional. So each vector is an eigenvector, so you really can't sum the eigenvalues. So trace is not defined, but trace is defined in terms of distribution. So that's the key idea which will go into the proof. I just wanted to make this clear. So that generalizes the idea of finite group trace and the character of the representation in this way. And then you can see that if I apply the conjugation operation here, so for example, suppose group G is acting on such functions by conjugation, the support will just change to the conjugated support, so it remains compact. Then you can see that chi pi f won't change because the way we are integrating, you're going to get certain sum, the analog of that sum, and you can see that the conjugation doesn't affect the right-hand side. So it's a conjugacy invariant distribution on G or linear map on CC infinity G. But remember that this is not an operator. We are already calculating its stress. And now let me just relate this with the first example I looked at. So there, it's not a semi-simple group clearly. It was Rn. But here the Poisson summation formula now can be related to this comment. So I'm going to excuse myself by declaring that all the Haar measure normalizations may not be correct, but there is a certain canonical way to do it. So I'll not worry about the constants appearing, multiplicative constants which appear here and there. So the theme is something like this. You have the representations, so the unitary representations of Rn. So let me call it Rn dual. So this will be isomorphic to Rn via, if you take any vector y here, you look at x, the vector x going to e power 2 pi I inner product of x and y. This, let me call this xi y. So this xi y is going to define a unitary representation on Rn, and every unitary representation on Rn will be, if it is irreducible, it will be one-dimensional and given by xi y. So the Poisson summation formula, you saw f hat getting evaluated at real numbers in the classical Fourier way. This is indeed, you are calculating trace of the one-dimensional unitary representation xi y, because you are essentially the Fourier transform is multiplying such a given function by such a character and calculating the value, calculating the integral. So that also belongs to this class or this theme, though the group that we started with was abelian, not semi-simple. Yeah. And of course, finite group theory is even more simpler. There one just gets the usual calculation of trace. Okay, so these are some of the setups. Now I'm going to come to a certain result which me and my advisor proved long time back, 15 years back already. And I continued working on some variations of this theme over the last few years. So we called it spectral strong multiplicity one theorem. Now people familiar with the literature of strong multiplicity, sorry, of automorphic forms and modular forms. So what is the strong multiplicity one theorem? So there are two versions. One is for the cusp forms, which I'll not show in the slides, but I'll say it orally. So you have some suitable, let's say, cusp forms with, I think you have to assume eigenforms, such that it's their eigenvalues. So let's call them APF and APG, the Fourier coefficients which appear in the expansion. If APF and APG are equal for all but finitely many primes, then the cusp forms themselves have to be equal. So this is called Atkin-Lehner strong multiplicity one theorem. And the adelic version of that says that if you had two automorphic representations, cuspidal, such that their local components agree almost everywhere, then the automorphic representations are equal. Further, they appear with multiplicity 1 in the L2 decomposition. So that part is, it does not have an analog here, but yeah. So you'll see the theorem and then you'll connect that with the automorphic or modular form version. Yeah, so the definition of representation equivalence is reformulated in using the term representation spectrum. So you look at the set of multiplicities together with this set of irreducible representations, which such that multiplicity is positive, together with the multiplicity function. So this is thought of as the idea of spectrum. And now, yeah, my comment is what I just said. What we are going to see in the next slide is going to be the analog of that in the context of linear connected. Now, let's work with non-compact semi-simple Lie groups, because for compact semi-simple Lie groups, the kind of lattices you get will be finite, and then that's less interesting in the context of differential geometry there. Or yeah, let's say that it's slightly differently behaving things. So let's stick to the non-compact case. But it could be of higher rank. So SL2R is a rank 1 Lie group, but this theorem applies to a larger class. So you assume something like what you have seen in the Atkin-Lehner theorem, that you have a finite set of irreducible representations. Outside that set, if you pick up any pi, then the representation has same multiplicity for the two lattices gamma 1 and gamma 2. This is the hypothesis. And the conclusion is that indeed the L2 G mod gamma 1 and L2 G mod gamma 2 have to be isomorphic in this case, namely all the multiplicities must match. So the theorem and the proof relies on the important work of Harishchandra, which I like to state the main results here. So the crucial idea was this, that the trace that we defined by this chi pi f. So we looked at the convolution operator pi f, which shown in the slides earlier. Finite groups case, it will look like this. So its trace exists and it's given, so it defines a distribution, and that distribution is given by such a formula. So yeah, when you stare at the right hand side, I start with some function h, we have to assume something called locally integrable. In this context, it will mean that it's a nice measurable function, so that on each compact set, the integral is finite. So it could be a continuous function whose total integral may not be finite, that's okay, but we just need locally integrable condition. And now if you start with any such h, then the right hand side is going to define a distribution. So there is some theory of distributions on spaces, and it generalizes to groups where you, so I'll not go into those technical definitions, but the thing is that given a function, you evaluate it against another function, and that gives a nice linear map. And the question is that, for example, given chi pi, given irreducible unitary representation pi, is chi pi given by such a function? And the answer is yes. So this is one of the strong results of Harishchandra. And now, staring at this, it will be kind of clear. If you calculate the trace of this side, this will be what we called as chi pi f. And this side, it will be just integral of f against the function called chi pi, which was the trace function there, the character. So the character integrated against the function f gives you the trace of convolution operator. And for finite groups, it's straightforward. But here, there is something called trace function. So you have to define it as a distribution. And it's given by this. So now let's also look at another result, which basically says that these distributions are in fact linearly independent when you are looking at distinct mutually non-equivalent, pairwise not equivalent irreducible representations, for which they are linearly independent. So both these will be used. So in next 5 minutes, I'm going to give you a very broad outline of the way the theorem was proved. And later, I'm going to talk about some generalizations of this in the recent works, where this idea was sort of similar, except depending on the context, we had to choose our functions and work out a little differently. But the theme is something like this. Now, let me go to the trace formula again before looking at the outline, because we'll have to see what kind of things come here. So now I mentioned that to get the trace formula, one has to calculate the trace of convolution operator in two ways. The convolution operator was for the whole right regular representation, which breaks up as discrete direct sum like this, except it's an infinite sum and you have to complete the corresponding spaces. But if you apply it on one function f, then because our f was compactly supported and all nice things, the trace will actually break up as some infinite series of this kind. So remember that this pi is varying over all irreducible representations of G. We don't know whether chi pi f will be, in general, it's not true. Chi pi f may not be 0 at any of them. So it's indeed, it can be indeed infinite series. On the other hand, under the hypothesis of our theorem, we'll compare the left-hand side for two given lattices and make it simpler. On this side, there are some constants appearing, which I'll like to highlight them a little bit. So let me write down the pi f again. So this is going to be integral of this kind. The integration is happening over G mod gamma. First integral is happening over G. But now remember that our functions that, so for example, so if I apply this on one particular element of L2 G, that will be another function. So in some sense, you have this pi x phi function over here and then integrating over G. Now the things simplify in the following way. Your function phi is going to be left gamma invariant. So this integral will split as a sum over gamma and an integral over G mod gamma. And ultimately, with all that, this pi f will be given by a certain integral of this kind. And one has to be a little careful with various things going on here. I'll be a little sloppy here, but you get the idea. So these are called integral operators. So you are going to integrate your function with a certain kernel function, and this kernel function is going to be nothing but the average of the function phi that we have started with here. Phi of something like x inverse gamma of y, where gamma runs over gamma. So if you, yeah, so there will be a sum over gamma here, and this integral will come over G mod gamma now. And with the correct calculation and all those things, one finally arrives at something like this, which I'll explain a little bit. So you first go to the next slide where, so the integrals which appear in this ultimately are going to be integrals over the conjugacy class. So now you can go back to your basic group theory, which you learned few years back. The conjugacy classes are homogeneous spaces where they look like G modulo the centralizer of gamma in G. And here we are working with locally compact groups, not merely abstract algebraic abstract groups. So here they have a Haar measure on G, and then this again descends to a Haar measure on G mod G gamma in the case we are looking at, which is the unimodular locally compact groups. In fact, here we are looking at semi-simple Lie groups. And then this G mod G gamma can be thought of as a homogeneous space on its own. And we are integrating the function f on that homogeneous space, which is like integrating function on the conjugacy class. In the induced representation of finite group formula that I showed, you are summing over conjugacy classes and then on each conjugacy class, you evaluate the trace function. So something like that you can do here, except your function itself is not conjugacy invariant. So you integrate it, and such a thing is called an orbital integral. You are integrating on the conjugacy orbit of an element. And then such orbital integrals show up here because of this sort of sum. My f, and so here the f was a compactly supported function, and phi was the vector which has now gone away in this last stress calculation. And then there will be some volume term which will show up because on you have to go through this whole derivation and you'll see how this volume term shows up. So these are the quotients of the centralizers of elements in G modulo centralizer in gamma. And then you have to look at all those gamma prime who are conjugate to given gamma and so on. Yeah. So the ultimate story is that it will be sum of such orbital integrals. And remember, orbital integrals are also nice distributions on F on G, and they're evaluated at a compactly supported smooth function. So this is the way trace formula is obtained. And now going back to the case at hand, where we are looking at the proof of strong multiplicity one theorem. Now the way the trace formula is getting used here, you apply the trace formula for a function for the given lattices gamma 1 and gamma 2. And then the hypothesis was that only finitely many such terms survive. Okay, so you are indeed going to get a finite linear combination of elements of the type chi phi as distributions on the left hand side. So this applies to every function, and remember that this number is 0 and doesn't depend on what function you are looking at. This number is 0 outside S, and on S it will stay, and S is a finite set. Yeah, so that's the idea. So you get a finite linear combination of chi pi f kind of distribution of the type chi pi on the left hand side. Now you can immediately try to relate it to the theorem which I stated, which says that for inequivalent representations, irreducible representations, the chi pi's are linearly independent. So if you want to show, ultimately the aim is to show that this term vanishes for all pi. So it should be sufficient to show that for some suitable function, the right hand side is 0. That should be enough. And now remember that the orbital integral was calculated on conjugacy classes. So suppose we choose a function which is suitably away from all these conjugacy classes appearing, then clearly the right hand side is 0. So you localize your problem. So this is very analysis themed proof, except we use very strong results in Lie groups and representation theory. So you have to find suitable functions which are nice in the sense that they're compactly supported, smooth, but are going to vanish at the sets that at the conjugacy classes that we are considering. Then we are left with such a thing, what I just said. And now here the idea is that the chi-pi's are given by some integrating against some fixed function pi. So you are going to take those finitely many elements in S. They will give all of them will give functions, and you take the sum with the multiplicity factors, and there's going to be some function phi for which this is going to be true, and then that will tell you how to choose your how to choose these functions so that the right hand side vanishes. So I described here. So you take any smooth and compactly supported function supported outside the union of these conjugacy classes, and in this case, not difficult to believe that you are looking at G and you are going to look at the centralizer. The centralizer is not finite, and because of that, the G mod G gamma will always be of smaller dimension and hence measure 0 with respect to the Haar measure. And that's why there's a measure 0 set that you are going to get there, and the countable union of such conjugacy classes appears. So you should be able to choose a function which is away from that. And then for such a function, some small technical calculation will tell you that the character distribution, the sum of character distributions is given by integrating this function phi. So it will prove that phi itself has to be 0, and hence hence all the multiplities are equal. All right. So just wanted to give a glimpse of the main idea to choose a suitable function which will be 0 outside those conjugacy classes. Okay, so now after that, there's a slide where I very briefly described some of my recent work, but now there is some time left, so I'll go over some details of that. Okay, so if there are some questions, please stop me and ask. Slightly, I'm going to change my track a little bit. But the theme will be like what I said here. Okay, so let me not go to the next slide. Instead of that, let me say a few things here. So our setup will be like this. You have a group G, which is real, semi-simple, connected, and all such things. I think we also assumed linear to get some results right. So real, semi-simple D group. Keep the examples of SL2R, and for this discussion, the next discussion, sometimes you have to look at the rank 1 case, where again SL2R is one prototype example. So you start with this, and then there is a concept of maximal compact subgroups of these. So in, I think, Raghuram's and Tiloin's lectures, you saw the case of GLN, where they looked at a thickened subgroup which denoted by K infinity. Here, since we are working with G, which is real semi-simple, I'll just look at the actual maximal compact. So in SL2 case, it will be SO2 and so on. And maybe I'll take the connected component. So I'll take K0 analogously. In the case of SL2R, there is no need. The maximal compact is already connected, but in general, it might be, it's better to look at K0. But nevertheless, let's assume, keeping SL2R example in mind, let's assume that we are in the case where K is K0. Now you ask the question, so there are some representations, let's say some irreducible unitary representation of G, the Lie group. Now you ask the questions, what happens if you restrict it to K? Okay. So some of you are familiar with the compact group representation theory, but if not, then just take the following fact as some well-known fact about compact Lie groups. So the pi restriction to K is going to decompose. I'll use some different notations now, maybe M dash, or maybe M sigma is fine. So this is again some sort of Hilbert direct sum, let me call it completed direct sum, where because we started with an irreducible representation, it's something called admissible, and all these M sigmas are going to be finite. So as a irreducible decomposition over the compact group K, it will look like this. Yeah, so here you don't need, there is no gamma or anything coming originally. Since K is compact, this will be true. Yeah, so it comes, it's a consequence of something called Peter-Weil theorem. Now you ask the question, which representations of K appear here? In particular, one simple question will be, what is? So yeah, you start with this pi and you look at the invariants of pi under k. So which means in the representation theory language, k is acting on that and you are asking how many times the trivial representation appears here. So what is the multiplicity? So the dimension of this thing will be the multiplicity of the trivial representation. So so suppose it is non-zero, such a irreducible representation of G is called a k-spherical representation, and we suppress k by assuming, by defining it in the beginning, and we think of this as the spherical representations of k. And then there is a very nice connection between the following thing. So maybe I'll say a little generalization of this and then talk about the relation with eigenspaces of some operators. So similarly, we can ask the question, what is the, I mean, rather than what is, what I meant is, let's say, hom tau comma pi non-zero. So asking the dimension of this invariant space to be non-zero is same as asking hom trivial comma pi, is it non-zero? In general, for tau, I think I called it sigma, let me keep sigma. For a given irreducible representation of k, does that appear in this decomposition? Which is same as saying that is hom sigma comma pi non-zero. So let's call such a thing as sigma spherical, and in our next slide you will get sigma replaced by tau. So for any irreducible representation of k, you can ask the question, is your pi tau spherical? And now these things are related to the idea of homogeneous vector bundles and differential operators on them. I hope this part will be well visible in the end. I'll just draw some small diagram, nothing, no cohomology diagrams in my talk today. So let's start with, let me write the example which will appear at many places. You can think of SL2R as isomorphic to another Lie group called the non-indefinite orthogonal group SO21 with the connected component. So this can be thought of as the isometric group of the hyperbolic space, and in general this 2 can be replaced by arbitrary n, and then you can think about this as one nice group to work with. It won't be SLN in general, it will be a rank 1 Lie group. And then so start with such an example for now. And here here there will be an SO2 copy inside SO21 connected component, which will be a maximal compact. So, and you can do the same thing that we're starting with earlier. You look at a discrete subgroup of compact quotient here. So the basic G mod, K mod, gamma kind of space will be here. And now there will be vector bundles over this. I'll just call them as X tau. So this is the homogeneous vector bundle. Corresponding to tau, where tau is an irreducible representation of k. This is my k, this is my g. In general, it will look like this. Keep the example to understand the things better for this. So what is this homogeneous vector bundle? You look at pairs of the kind G, some element in G and some element in this vector space corresponding to tau. And then there is some identification you do with respect to the k action, and you get a vector bundle. And the broad idea is that the smooth sections of this vector bundle correspond to the induced representations of certain kind. And you can talk about the Laplace operator, which corresponds to the Casimir element of the Lie algebra here, and that will define an action on the smooth sections. And you can ask the question. So, for example, how does its eigenspace decomposition look like? And those multiplicities are related to the multiplicities of sigma there. So this part is a little difficult to write down with all the details, but I'll try. The correspondence goes something like this. You start with a real number lambda. Typically, in this case, all the operators are positive definite. So we are going to get non-negative real number to start with. And such a lambda will correspond to a certain representation. So let me stick to the SO2, 1 or SON, 1 or rank 1 case. In that case, at least you will get a certain representation which will be denoted by tau sub lambda. Not tau, let me call it pi sub lambda. So this is going to be a principal series representation of G, which is obtained by a parabolic induction process. G is the Lie group that we are looking at. And the multiplicity of this lambda, I'll call it spectrum of the Laplacian corresponding to the setup. So Laplacian G mod K, let's say. So this lambda is going to appear in the eigenvalue decomposition or the spectral decomposition of the Casimir acting on the sections of that bundle. And you ask the question whether the multiplicity is finite, and if it is, what is that number? So this multiplicity is in fact going to be related with the multiplicity of pi lambda inside our L2. So you had this L2 G mod gamma decomposition that we looked at. So what is the multiplicity of pi lambda there? Okay, so there is a bijective correspondence between the the eigenvalues which appear in the spectral decomposition with the corresponding representations which appear in the L2 G mod gamma. So this is like, so far we are only looking at the irreducible unitary representations. Now we are looking at certain subclass which is given by the principal series. They correspond to the Laplace eigenvalues. And in the classical Selberg test formula, which I showed a few minutes back, there you look at all those eigenvalues appear there in the spectral site. And the function was taken so that, for example, in general also that function can be function on which we are applying the test formula can be taken to be invariant under or equivariant under certain actions of K on left and right. And then the test formula, you'll only see the corresponding principal series representation showing up. Only those multiplicities will show up there, and the test formula simplified. Now, using all these themes, I'll now just briefly tell you the kind of results which were done recently. So the first kind of results, which is what I just briefly talked about in the last 5 minutes. So with my collaborators, Gunja Sachdeva, as well as Gunja and my PhD student Kaustubh, who is also attending this meeting. So in a joint work with them, we proved some generalizations of what we saw here in the context of tau spherical representation. So tau spherical is written over there. The homomorphism space between tau and pi and over K is non-zero. So for such representations, can we write a strong multiplicity one theorem? So the shape is slightly different because these taus are not self-dual. So tau and tau dual both we have to consider in that. If tau was trivial, then this result was proved in my thesis with as a joint work with my advisor. But for non-trivial tau, in general, they are not self-dual, and hence tau and tau dual both appear in the statement. But these are the analogs of this. And the context was general. Yeah, we also went beyond the beyond the rank 1 situations. In rank 1 situations, you have some more interesting Riemannian structure here. There will be the hyperbolic spaces with negative curvature, constant negative curvature. But in general, our methods also apply there. We get it. And then recent work with Kaustubh. So there we want. So the idea was to go beyond the co-compact case, which is of more arithmetic interest. The examples like SL2Z and congruent subgroups, they are not with compact quotient, but they are with finite volume, co-volume, and some partially. So we have partially succeeded in some cases, but the hypotheses are not as strong as that we wanted in strong multiplicity one theorem. So this is one recent work which I recently submitted, yeah, we got some analog of strong multiplicity one theorem there. And there one can work with reductive and semi-simple cases separately. In reductive cases, sometimes you have the determinant character, and using that things simplify a little bit. But yeah, so our thing is not the most general thing and which would have wanted, and the problem is in some sense still open. How should one state how should one formulate the multiplicity one theorem in the context of general finite covolume lattices. So the main challenge is that the analysis is much more harder. So in the compact case, the very let's say satisfying result is that our L2G mod gamma breaks up as direct sum. In the general case, as you know, it will have a continuous component as well as a discrete component. And the continuous component is definitely difficult to handle with. The kind of direct integrals you get in the context of arithmetic lattices in semi-simple Lie groups like SLN and so on, and reductive groups like JLN, the Haar measures are, sorry, the measures, spectral measures that you get on continuous part are easy. But on the other hand, orbital integral side is also more complicated, and there it needs a lot of delicate analysis. So with that, the hope was to get something like what we wanted, but we haven't succeeded completely, but some partial results. All right, so thank you, and yeah, I'll take question.
Are there questions or comments? So first I want to thank you for this nice lecture and maybe make a very nice question.
Sure.
So the first time you see the Selberg-Price formula, so you see on one side a sum over eigenvalues of Laplacian that you have no idea how you may compute. And on the other side you have an even more doubting thing, the sum over the lengths of geodesics.
Yes.
So you have the impression that you have a theorem that tells you that some quantity that you have no clue how to do is equal to another quantity.
Sure.
That you have every less clue how to do.
Yeah.
On the other hand, in this talk, we have seen a very nice application of it. It's at the heart of your.
Sure. Yeah.
But is it possible, for the sake of the young and the not so young, to give a more or less elementary application of the original Price formula?
So yeah, so one application which is again more into the analytic number theory aspects. So since so all of us know what is prime number theorem, which gives the estimate on counting primes of certain size. So there's an analog of this for the Riemann surfaces that we are getting here. So we are getting a Riemann surface of the type hyperbolic space modulo a discrete subgroup with compact quotient. So it will be a compact manifold. You can talk about how many geodesic classes are there of a set length less than equal to something, and then you ask the question how it asymptotically behaves. That's called prime geodesic theorem. So the original Price formula by Selberg was one tool to prove it. The other aspect is you can ask how eigenvalues grow. So on the left-hand side, you had a discrete sequence of eigenvalues increasing to infinity. And you can ask the question, how many eigenvalues are less than equal to x, and how does that function grow? So these are called Wiles' law of the eigenvalues. In the context of SL2Z and SL2R, this was stated in the beginning. So depending on what one is interested in, so the Price formula as such is definitely useful in these both directions.
Then another question in the proof you were explaining, at some point you say, okay, the conjugacy orbits of gamma are sets of measure zero, and then I need to find a function with compact support, smooth, that is zero at this.
It avoids the, yes.
But now you have a countable set of measure zero sets, no? Because
yes.
if I understand, you have but then
so these they correspond to discrete subgroup gamma. So it's still a countable union.
Yeah, but it's countable. But I mean, if you have a countable set of measure zero, it might even be dense. So how you know that you can find?
Yeah, exactly. So that just measure zero is not enough. They're coming. So I also made a comment that you are going modulo. So G is your, let's say, k-dimensional group, and then G gamma will be of lower dimension, but also non-zero. So G mod G gamma will also have less dimension. So using that, one shows that it cannot be dense. And
so any other questions? So if not, let's thank the speaker again.
Yeah. Thank you.